Okay, we are entering this. I guess for this unit we could call this the states of matter. And we are going to be, we're going to be starting with the enthalpy change of phase changes. So let's focus in first on changes of state because it's a good transition from where we were last time in thermochemistry. Normally I'd include this in thermochemistry. We didn't have enough time to put it in the last unit. Changes of state. Now, if we make a graph, and we're actually going to do a lab with this on Friday. We're going to do a lab activity. It's not a full lab report lab, but if we make a graph like this, and if this axis is Q, why did I put it way over there like that? You want it to be fairly long on the x-axis. Q, you know what that is, right? It is heat added. So this is heat added to the system. Remember that Q is not a state. Q is not like temperature. It's not a state of matter. It's some stuff that's being added. So as we move along the x-axis, what we're saying is the amount of heat added is increasing cumulatively. On this side, we're going to put temperature. We're going to put temperature in degrees C. Now, I'm going to put 0 degrees C here. And up here, I'm going to put 100 degrees C. Now, if we start, this is for water. Actually, let's put a nice title up here. This is going to be the heating curve of water. And it is our model for changes of state. The heating curve of water is our model for the changes of state. We're going to start with some really cold ice. Okay? So it's going to be down here. Notice the temperature's below 0 down in the origin here. As I add heat, here's what happens to the temperature. The temperature rises linearly. This is ice, solid water. The temperature rises in a linear fashion as I add heat. Actually, I could calculate that amount of heat. Q equals mc for ice delta T. C for ice is a little bit different than C for water. What is it, 2.1? I want to say. Yeah, 2.1. So C, instead of being 4.18, is 2.1 joules per gram per degree C. All right? Keep that in mind. Those numbers will be given to you, but just keep it in mind that it's different than C sub W. Now, as I continue to add heat, once I have raised the temperature of the ice to 0, something different happens. Now, the ladies already know all this stuff. That's the explanation. Okay, so as I continue to add heat, this happens. The temperature doesn't change. There's actually a big swath of the x-axis where I'm adding heat, but the temperature's not changing. How can that be? Josh?
It's changing from one phase to another?
Yeah, apparently. And now on this line right here, what's happening is the ice is melting. Apparently melting takes energy. Makes sense, right? What's happening here is that Q is equal to the moles of ice times something called the delta H of fusion. Now the delta H of fusion is the heat required to melt 1 mole of the substance. change it from a solid to a liquid. This energy, or this is the energy required to break the ice structure. Partially break the hydrogen bonds. Yes. That's a little FUS. Sorry, yeah, that should say FUS for fusion. This means fusion, which means melting. Fusion is melting. So let's look in a little bit more depth. So I'm going to go down below here, and we're going to look at kind of a rudimentary molid of a solid and a liquid. A rudimentary model is what I meant to say. In a solid, you have molecules or atoms locked into a rigid 3D structure. They are able to vibrate in place molecules vibrate in place. That's all they can do because they can't move around. They can't slide around one another. They're stuck. They can just vibrate in place. And this is actually why solids have a low entropy, because there's only so many ways to distribute the energy in the material if the only way they can have energy is through vibrational energy states. Now in a liquid, though, we have a little bit different situation. Here, the molecules are also free to move past one another and slide around. So molecules, not only can they vibrate, they can vibrate in place and move around. Basically, they're sliding past one another. Now leave some space over here because we're going to come back to the gas state later. This transition involves the partial breaking of the hydrogen bonds. In other words, the hydrogen bonds are not going to be active for as much of the time, I guess you could say. I'm not sure exactly how we'd say that, but it's a loosening maybe of the hydrogen bonds, something like that. You can see that we've broken the structure. It takes energy to break things, right? If you smash your car into a tree, much of the energy of that impact will be absorbed as the front of the car crushes. And that's actually kind of a safety feature, that your car will crunch up, absorbing a lot of the energy like a spring or like a shock absorber. You wouldn't want your car to be perfectly rigid, because then if you crashed into a tree, it wouldn't absorb any of the energy, the impact. That would be left for you to absorb, or it would be transferred to you as you flew through the windshield. Right? You won't fly through the windshield because you'll have your seatbelt on. Very good. Okay. Anyway, let's go back up to our picture. So what happens is the temperature doesn't change even though I'm adding heat until I reach this certain point right here. Oh, by the way, what is heat of fusion for ice? Delta H of fusion for ice is 6.01 kilojoules per mole. So it takes 6,000 joules for every mole to melt the ice. That's quite a bit. 6,000 joules per mole. So once we hit here, though, all the ice is melted at this point. All the ice is melted at that point. And then we start going up again. Now the slope is going to be a little bit different. It's going to be shallower because C is different for liquid water. So this should be a line, sorry.
So should it be steep
It should be shallower than ice. Not as steep. Yeah, I should have made ice steeper, but anyway, this slope should be less because C is greater. So in this portion right here, this is what we've been doing these calculations already, CW delta T. The heat added is a linear function. I mean, the temperature is a linear function of the heat added. So if we were on this line, we've already done problems like this, heating water up from one temperature to another. We've done those types of problems. The only type of problem we haven't done actually is this. We've done heating materials with Q equals MC delta T. Now what's happening in this part? We're just heating up the water. So this is heating water, heating liquid water. Now let's focus on that for a second before we go to the next stage. When we heat water, and I'm going to say here where there's no phase change, so we're not changing it from one phase or one state of matter into another. When we heat water, what's happening is the particles are simply speeding up. So the energy is being used to speed up the particles, make them move faster. So that's a linear function. Basically, whatever energy you put in is being added to the average kinetic energy of the particles. Temperature is directly proportional to the average kinetic energy. Okay? This is proportional to. I guess it's really like this little thing here. It's like a little thing like this. It's like an insect that's like trying to bite you. Yeah, it's kind of a little thing like this, I think. It's proportional to the average kinetic energy. This is the average. It's actually the geometric mean, but the average kinetic energy of the particles. Now, what you want to notice about this, and this is temperature, it is not equal, okay? It's not the same thing. There's some constants in there, constants of proportionality. It's proportional to the average kinetic energy. So the higher the temperature is, the higher the average kinetic energy. One of the things you'll notice if you look at this, I don't know, most of you didn't have IPS, but kinetic energy is 1/2 mv squared, where this v is the velocity. So look at the other term that's in kinetic energy. It's the mass of the particles. Remember we did the Dulong and Petit lab? And we found out that the molar specific heat was the same, pretty much the same for all of them. Yet their specific heats in terms of mass were different. Here's your answer why. If a particle has a greater mass, it will have a greater kinetic energy at a given temperature. So that's what's happening in this linear portion of the graph, and I'll go back down there in a bit. Once we reach 100 degrees C for water, that's the boiling point, of course. Okay? Once we reach 100, it's going to go level again. And this is a long level curve. I can't really make it as long as it should be because it's 40.7 kilojoules per mole. So in this portion right here, Q is going to be equal to the moles. Moles of what? Lead? Water. We're talking about water. If we were making a graph for lead, then this would be moles of lead. Okay? It's going to be moles times delta H VAP. What do you think that means? VAP. Vaporization, right. This is the heat required to vaporize 1 mole So it's going to be in kilojoules per mole, and then it will cancel with moles, and we've got Q. One of the things you notice is that it's actually a simpler calculation when you're in the level portions. Moles times one number, delta H of fusion. For water, delta H of fusion for H2O is equal to 40.7 kilojoules per mole. To vaporize 18 grams of water requires 40,700 joules. To vaporize 18 grams of water takes 40,700 joules. Heat required to vaporize 1 mole. Now, once it's all vaporized, so this is boiling right here. And of course, when we're boiling water, it's going from a liquid to a gas. Once it's vaporized, then we're going to go back up like this, and I think it's actually a steeper slope than the ice even. I think it's whoops, looks like a curve. That looks like a curve. How come I can't draw a line? This is weird. 40.7. All right. Let's pop down to here and finish our little diagram. Phase change from a liquid to gas involves a transition from sliding particles sliding past each other, to particles flying in straight lines through the air. Gas, particles fly in straight line paths. Through empty space. Did you know that the air particles in this room are flying through empty space? The oxygen molecules and the nitrogen molecules in this room are flying through space where there's nothing. Empty space is actually in between those particles, right? It's kind of weird to think about. I never really thought about that before. Okay, anyway. Now, these can have a lot more ways to have energy. When you're talking about the energy of straight line motion, there's a lot more energy levels, and we talked about this a little bit with entropy. That's why gases have so much more entropy, because the particles can be going at all sorts of different speeds. With vibrational energies, it's like you can vibrate this fast, this fast, this fast, this fast. At the atomic level, it's quantized, and there's not a lot of vibrational energy levels. But with translational energy, this is what we call translational energy levels, they're much more finely spaced. There's more freedom of motion. Let's write it this way. If I'm going like this is more freedom of motion. Here's an illustration. Right now, you guys are a solid, okay? In the public school system, we make students into solids. We freeze them into solids. You guys are a solid right now. You're all sitting in place in your desk. You can move in your desk, but that's all you can do, okay? You can't get up and move around, or I'll yell at you and give you detention, right? Now, to turn you into a liquid, what would I do? I'd give you all swivel chairs, and I'd let you just roll around wherever you wanted. Okay? That would be a liquid. To turn you into a gas, now you would have more freedom, there's no doubt. In fact, I could say maybe a liquid is you being able to walk around wherever you want. Okay? Maybe you don't have to ask to go to the bathroom.
The gas would be just like flying.
Okay, so what is the gas? The gas is Peter Pan. So for the gas, you all become Peter Pan. And you're all able to fly up into the corners of the room and fly out the window and fly to China or wherever you want to go. Okay? Now, again, in the phase transition, here, to get from here to here, we have to totally break the hydrogen bonds. So that's why it takes 40,700 joules to vaporize 1 mole of water. You have to actually rip those water molecules apart. Remember the hydrogen bonds? It's the intermolecular forces where the hydrogen of one molecule is attracted to the oxygen of another, and they can get in real close, so there's a strong attraction. You got to rip those apart. Okay? And it takes energy to break things. Making bonds releases energy, breaking bonds requires energy. Now, what happens then once I'm up into this range here? This is steam, the final stage. It's not really the final stage, but steam. And here we have Q equals mc for steam delta T. C for steam is 1.84 joules per gram per degree C. So it's lower than the specific heat of water. Now let's look at this graph a little bit. It's a little distorted. This line really should be longer. Okay, that vaporization line should be longer, and so should the melting line. Did you know that, I don't know if you ever heard this, but steam burns are very dangerous. So like, say workers who work over there at UConn's power plant where they make the steam that goes under the ground, very dangerous to get a steam burn. Why would that be the case? It has to do with energy. Two things happen when the steam hits your body. One is the steam, so let's say the steam is up. By the way, you can make steam as hot as you want to. The only limit on how hot steam can be is the plasma transition, where you would destroy the molecules. All right? So you could be way up here. So let's say you start up here, you've got some really hot steam. Maybe it's like, maybe the steam's like 200 C or 300 degrees C. By the way, you want the steam to be hot because the greater the energy difference, the more efficient the heat transfer is, and the more rapid it is. So this thing is going to, when it hits your skin, what's going to happen? It's going to come down, okay? Same thing would happen with hot water. You get hot water on your skin. This is the heat that will be transferred to your skin. But then something else happens. It's not steam anymore, right? As soon as it hits 100, it's going to go bam and turn into water, liquid water. And all that 40,700 joules per 18 grams is going to get transferred into your skin. So instead of just having the little amount of heat to cool off the steam, it's that plus this huge chunk as it condenses into water on your skin. It's going to be used to cook the proteins in your skin, denature them, right? Those outer layers of skin will detach from the layers beneath and it'll like slide off your arm. Okay. So this is a picture of the graph, and I would say you want to memorize this thing in terms of its structure and what are the equations, because what we're going to do is problems where instead of just saying how much heat, what we used to say in the last unit I would ask you, how much heat's required to raise the temperature of 100 grams of water from 25 to 100, right? You did problems like that last time. But now what we can do is we can start down here, and we can go all the way up to here and figure out the heat required. All we do is 5 different equations and then add them up together. Okay? Let's look at an example. Example calculations with the heating curve. Example calculations with the heating curve. Starting, or let me say it this way. How much heat is required to raise the temperature of, let's make it simple, 100 grams of water from room temperature, 25 degrees C, to 125 degrees C. Now, when you look at this question, you need to always have in your mind, when you're talking about a substance, and now that we know we could be talking about a phase transition, what are the boiling points and freezing points? You have to know that. So when you look at this question, one thing should jump out at you. 125 is over the boiling point of water. Because if you don't recognize that, you're going to try to do it all with Q equals MC delta T, and it won't work. All right? You can't do it just with Q equals MC delta T and use 100 degrees C as your change. You can't, because here's what we're talking about in this problem. In this problem, we are going from about right here to about right here. And so you've got this amount of heat, this amount of heat, and this amount of heat. You've got 3 sections of the graph that are all governed by different equations. And then you just add them together. It's really not that difficult. It's just you got to do 3 separate equations, you add the result. It's additive. So let me show you how it's done. We've got one step where it's going to be Q equals MC for water delta T. And this is going to take us, so I've got 100 grams I said here. We know that C for water is 4.18 joules per gram per degree C. This is the liquid water portion. This is when we're between 25 and 100. And then we're going up by 75 degrees C here. We've got a change of positive 75. Why 75? Because I'm only going to 100 in this step. In this stage, I'm only going to 100. You with me? So I've got 100 times 4.18 times 75 gives me 3135. I've only got 2 sig figs here, but I'll keep them for now. Joules. That's how many joules it takes to heat up the 100 grams of water 75 degrees. Do you know that in reality, C actually depends on the temperature? That sounds interesting, doesn't it? So, which tells you that you really have to use calculus to do these problems. We just approximate it by saying that C is constant. It's relatively constant. Okay, 2. Q is equal to the moles times delta H VAP. So we got to figure out the moles of the water. So it's going to be 100 grams times 1 mole over 18.02 grams. Aren't you glad to see the mole again? Yeah, you missed it, I know. We got to use it a little bit last time. And then this is per mole here. This is going to be 40.7 kilojoules. Okay, you should have a little red flag going up in your mind. I had joules here, I have kilojoules here. Keep that in mind. And watch your units. Right? So what do we got? 100 over 18.02 times 40.7. That gives me 225.86. I only have 3 sig figs here, so I'll underline those. Kilojoules. Look at the difference there. To warm the water up to boiling only took 3,000 joules. This one's taking 226,000 joules. That's to what? It's not really to boil it. To boil it is to bring it to boiling. To boil it off. To dry it out. To vaporize it. So have you ever been boiling water in the stove and you forgot about it? And you go back there and the pot is like red hot on the stove and it's empty? Never happened? That's what we're talking about. To actually take the water and boil it all off. Boil it to dryness. Step 3. Q equals mc delta T, and this is our 1.84 C value. So again, we have 100 grams. We've still got 100 grams of water. It's the same water. But now it's steam. And we're going to heat the steam up. So now we've got to heat the steam up. We change it all into steam. And we're going to heat the steam up. And it's going to be, whoops, what am I doing here? Sorry. I'm getting confused. Getting old. It's called getting old. And what's my temperature change? Plus 25, because I'm going up from 100 to 125 degrees. This is 125 minus 100. So I've got 100 times 1.84 times 25, 4,600. Wait, what did I do wrong here? Aha! Look at that. Made a mistake, sorry. I thought that was, I know it's a big difference, but that seemed like a really big difference. So made an error up here. Look at this. It should be 31,350 joules for the first one. It should be more. The temperature change is bigger. The specific heat is bigger, so it should be larger for the liquid water. Now the total Q is going to be, and you can do it either way. You can either convert joules to kilojoules or kilojoules to joules. I'm going to go to kilojoules because it makes sense to put my final answer in kilojoules. So I'm going to write 31.350 kilojoules plus 225.86 kilojoules. The underline is telling me those aren't significant digits. And then 4,600 kilojoules. And here nope, sorry, 4.6 kilojoules. Hey, I turned 42 this summer, guys. What's it going to be like in another couple of years? I'm going to be up here just babbling nonsense. So,
In a couple years.
31.35 plus 225.86 plus 4.6, what do we got? 31.35 plus 225.6 plus 4.6. 261.81 with correct sig figs. I'm going to go to no decimal places, so I'm going to have 262 kilojoules. Notice how it is dominated by the phase transition. It's dominated by the phase change. Phase change is dominating the process. Because look at the numbers up here. Look at my values. That's where most of this money came from, most of the heat. 226 kilojoules. This is 262. The difference was just the heating processes. So most of it was through the phase change. I want to show you one more quick example. How about going backwards? So start with 100 grams water at 25 degrees C and freeze it. Freeze it. Start with 100 grams of water at 25 degrees C and freeze it. Here I only have two steps. First I'm going to cool it down. Now be careful here because we got a negative temperature change. We're going down by 25, and then the next step I'm going to take and use the delta H of fusion. And it's going to be negative. Look at that. I just changed the sign of that just because I wanted to. I changed the sign of that because I wanted to. Why? Because I'm not really saying delta H of fusion this time. I'm saying delta H of freezing, or solidification, you would call it. So I'm solidifying instead of melting, so I changed the sign because the direction of heat transfer is going to be different. Calculate these and add them up. 100 times 4.18 times negative 25 gives me negative 10,450 joules. 2 sig figs. 100 divided by 18.02 times negative 6.01, negative 33.352 kilojoules with 3 sig figs. Now the total Q is going to be negative 10.450 kilojoules plus negative 33.352 kilojoules. Which is negative 44 kilojoules with correct sig figs. It's exothermic. Cooling that water down, it's losing heat. When it freezes, it actually gives off heat to the environment. This is just a 2-step problem. Last one was a 3-step. You could go as much as 5 steps. That is, if you start, say, with cold ice, warm up the ice, melt it, turn it to water, warm up the water, boil, vaporize it, and then warm up the steam. That's 5 steps. You'd have to add them all together. Any questions before I give you some problems to do? Questions?